Hello everyone, welcome back to lecture 14 of module 5. So we'll continue this lecture 14 here. So before I continue with the flood, let us talk about the water balance equation, because this is one of the very important aspect and fundamental that you need to know when you are working with the flood, right? So the water balance equation is a fundamental concept that shows the relationship between the precipitation, that is your input, and the output such as runoff, evapotranspiration, as well as the change in storage within the system, right. So here you see this particular equation. So the P, that is your input, right. So that is your precipitation. Then comes the Q, that is your runoff or stream flow, and the ET is evapotranspiration, and the delta S is your change in the storage. Now just consider this is a particular area, this is a cross section, and here the inflow can be your stream flow which is coming from the upstream, or it can be precipitation, right. So that is the input for this particular region or this particular area. So this is inflow, right. And then comes the output. What are the output here? So it can be runoff which is going down and we measure it as Q, then evapotranspiration, and then because of these two there will be change in the storage, right. So whether the level was here before the inflow started, and after the inflow maybe it will reach to this or maybe this. So this will be your delta S, right. So the change in the storage is equal to inflow minus outflow. It can be negative or it can be positive. If the inflow is more than outflow, then you will have positive change in the storage. If your inflow is less than outflow, then it will be negative, right. So to understand this water balance equation, I have used some of the numericals here. To explain the application of water balance equation, I will be using two different problems that we will be solving here to understand what is the application of this water balance equation. So the first problem statement is, for a given watershed, estimate average annual evapotranspiration using the following data, right. So here the knowns are surface area, that is given, right. Then mean annual runoff Q, that is also given. Then average annual precipitation, that is also given, and the time that we are going to use here, that is 1 year, and the delta S, that is the change in the storage, that is insignificant. So what we have to calculate? We have to calculate the evapotranspiration, right. So how we will do that? That we will try to learn today. So here you can see this is the stream that we are talking about, right, and here the surface area is given for this whole thing, right. Then mean annual runoff, the Q which is measured here, that is also given, and the precipitation in this particular area, it is also given, right. So let us start with the basic form of this equation. The delta S, that is equal to inflow minus outflow, and the inflow is your precipitation, that is given here, right, and the ET that we need to calculate. So ET plus Q, the both are outflow, right. So here the ET is unknown but Q is known. So ET is equal to P minus Q because delta S is insignificant. Now this Q we can change this form, and the Q you can calculate like this, and then ET will become 0.7 meter. Now here you see delta S is insignificant, that means there is no change in the storage. So here the inflow is there and evapotranspiration is there, right. So here 0.7 plus Q, that is here. If you add them together, that is the total discharge, total outflow of this particular system. Then you need to analyze what will happen if the situation continues to be like this, whether this watershed will be dry after some time or what will be the impact. So, the analysis is very important here. Then the next problem statement is, in a gentle hill slope, find the change in storage, that is delta S, right, of soil water using following data. So, here for this particular watershed, the surface area is given, rainfall intensity is given. So, intensity is 30 mm per hour, surface runoff is 15,000 liter for 40 minutes, delta T is 40 minutes, percolation outflow, that is insignificant, evapotranspiration is insignificant. Now, you need to calculate the delta S, right. So, we will start with the same equation, change in the storage is equal to inflow minus outflow. So, delta S is equal to infiltration minus 0 because there is no output, right. So, infiltration will be equal to precipitation minus runoff, right, and here the values are given and the intensity was given. So, you can calculate the precipitation, right. So, this will become 0.02 meter and then surface runoff is given. So, you can also calculate, you can normalize this 40 minutes and then you have infiltration is equal to precipitation minus runoff and this is 0.005 meter, right. So, this is how we are utilizing the water balance equation to analyze the situation of our watershed. Now comes the flood identification and mapping. So, this is one of the aspect which is very important. So, when we talk about this flood identification, it has role in early warning system, then it has role in effective emergency response, then protection of infrastructure, land use planning and development, risk assessment and mitigation, post flood recover and reconstruction, right. So, this identification is very important. So, here we will talk about the application of remote sensing, why we are using this remote sensing in the flood studies, right. So, as we know that remote sensing has the advantage and the first one is the large aerial coverage, right. Then second is the non-destructive data collection. Here we don't destruct anything, don't disturb the natural setting, we just try to capture the images and then we try to analyze them. And here the high spatial, spectral and temporal images are the advantages, because when we are having high spatial, spectral and temporal images, we have more information about the area or about the target, right. And this is also used for the inaccessible areas, because sometimes after the disaster we can't visit the area. So, in such situation remote sensing can be our eyes, right. Then real time and near real time data can be acquired, and if the sensor is active, it is continuously capturing and putting them into the archives. And the wide range of data, here we are having optical, microwave, lidar, UAVs, everything are involved in this particular thing. And the systematic and repetitive data collection. So, if we refer to a particular area, how a particular river channel is evolving with time, maybe we can use the Landsat data, because for the past 30-40 years we have continuous data, right. So, if you want to dedicate yourself to study a particular channel or a stream, that even you can do or perform using these satellite images. This is one of the example of inundation layers of 1998 to 2015 for Assam. This is from ISRO, it is available in the Bhuvan website, right. The satellite image showing Bees river stretch. So here you can see how this is changing, right. These are some of the example of application of remote sensing. You can see, so it is showing the water logging areas, right. This is for Mumbai. So when we talk about this flood modeling or monitoring or identification or forecasting, so there are different parameters that we need to study or we need to collect. So the basin geomorphology is one of the important parameter, then meteorological forecast or the meteorological parameters, then land use, land cover, soil moisture, the antecedent condition, then rainfall data, the precipitation, then if we have automated weather station data and the river gauge data that is required, then digital elevation model because we need to know the slope and aspect, and then flood data, the historical data that is also required here. And if that area has the snow cover, if the input is from the snow cover, then we need to include this snow cover in this analysis, right. So here you can see the different parameter observed in a study by Haldar to find the flood susceptibility mapping. So here you can see the elevation information, slope, TPI, TRI, TWI, relief amplitude, drainage density, distance to river, annual rainfall, LULC, SPI, MFI, NDVI, STI, geomorphology, and then MNDWI, clay content, lithology. All these maps were derived from the remote sensing data, and then he used them together to derive the or to map the flood susceptibility of this particular area, right. So here this is another example from indiavaris.gov.in. So here you can see this is the annual average rainfall across the Brahmaputra basin. These are some of the examples that I wanted to show because these are very important. Elevation information of the Brahmaputra basin derived from SRTM DM. So the SRTM DM earlier it was only 90 meter, but nowadays we also have 30 meter data, right. So this is available freely in their website. So you can visit the USGS website, the Earth Explorer, and then you can register and download these data sets. This is the land use and land cover distribution of the basin for the year 2005 to 2006 derived from IRS Resource-Sat 1 satellite data using LIS-3 sensor. So it is from the Bhuvan, you can download. The Brahmaputra basin predominantly features forest, agriculture fields, grazing land, tea plantation and waterlogged swampy areas or wetlands, right. So this you can download from Indiavaris, or you can also go to Bhuvan and you can download them. So when we have all these data set, then we can go for the flood monitoring and forecasting methods. So here we have snow melt runoff model, hydrodynamic model, rainfall runoff model or flow routing models, right. So these are different approaches that we are using to model the flood and forecast the events, right. When we talk about the snow melt runoff model, it is a hydrological model that helps to determine the runoff from the melting of the snow, right. Then comes the hydrodynamic modeling. It identifies the flood prone zone and improves the resilience of mitigation plans. Then rainfall runoff model, it helps to understand the processes in the water system due to changes in weather condition, vegetation and impervious regions, right. Then we have flow routing model, which helps to track the flood waves in a river channel and measure discharge, flow depth, volume, etc., right. So this is flow routing model. So there are different models in flood hazard monitoring and their suitability. In this slide, different models of flood hazard monitoring and their suitability is explained. So when we go for the physically based model, it works for flood hazard monitoring. flood damage assessment, probabilistic flood modeling, coastal flood mapping, flood monitoring, early warning system, right. Then we have physical models, which is for the flood risk on human, historical flood scenarios and modeling, dam break analysis, urban flood modeling, right. Then we have empirical models, which is flood hazard monitoring, flood susceptibility mapping, flood risk mapping, flood vulnerability mapping, emergency flood management, flood mitigation method selection. So, these are different approaches or different models that have been used in flood studies, right. So, when we talk about the advantage, we have precise identification of at risk areas, and then identifying vulnerable infrastructure that we can easily identify. Then it also improves the early warning system, safer and more efficient rescue operations, targeted resource deployment, effective evacuation planning, accurate risk modeling, and reduces future risk. So, when we have accurate flood forecasting, it has multiple uses. So, here this is one example from Chungthang Dam location. So, this is the Chungthang Dam. So, this is from NRSC. So, here you can see that this particular map and the details are available. So, I am just trying to introduce what remote sensing can do, how remote sensing can help, right, in this aspect. So, here you can see the flood map showing the change detection during the pre-flood event. The figure A, B and C are the zoomed portion of the rectangles indicated in the left river with the SAR image as background. The rectangles are overlaid on Sentinel-2 True Color Composite image on the top row and open street maps, that is OSM, in the other row, right. Here the flood map showing the change detection during the post flood event. Now, when we have the pre and the post, we can easily find what changes has happened during a particular event, right. Some of the examples of remote sensing application in flood studies and especially for the flood identification. So, this is again from NRSC. You can see that flood inundation, this is the Kopili river, right. This is another example where people have used Sentinel-2, and then this is for Ram Ganga river, and here they have utilized this microwave data Sentinel-1 and the VV polarization, vertical polarization, right, and for the same area how they appear, right, and the VH polarized SAR image is here. In remote sensing, there are two different domains, one is optical and another is microwave. So, let us try to understand what optical remote sensing can do and what microwave can do, right. So, this is a brief introduction. So, when we talk about the optical remote sensing, it has inundation mapping, that is the flood modeling mapping. So, we can have the visual interpretation, then we can also have the digital image processing techniques, and here it is mainly based on the color, texture, size, pattern and the shape, right, when we go for the visual interpretation. When we talk about this digital image processing, so here density slicing, image classification and different indices like NDWI, those are used to identify the flood areas, right. So, here this is one example by this particular paper. It shows the mapping of flood zones in Nasia watershed of Ghana, and here this is the figure, and the figure on the right shows the Landsat 8 precise delineation of the normal flood prone areas and the B, that is Landsat ATM precise delineation of the extreme flood prone areas. So, sometimes what happens, the same satellite cannot provide you all the processes. So, sometimes that particular time cloud coverage was there because we are talking about the optical remote sensing. So, if there is a cloud coverage, you will not be able to use them. In this particular work, Agnihotri et al. 2019, Sentinel-2 image taken during the flood and the Ganga and the Ramganga rivers altered courses are depicted in this Sentinel-2 image from September 14th, 2018. The yellow triangles indicates the location of the gauge station. So, here you can see these are the gauge stations, right. So, they have utilized this information and then they have used the in the flood studies. When we talk about this microwave remote sensing, so here in the urban case, so this particular slide will try to explain what happens during the flood situation and what are the advantages when we are having the microwave remote sensing. So, in the urban areas and in the forest area, how it works and how it is providing you the information. The backscattering will be from this place, right. So, this is the summary of microwave remote sensing. Now, here when we are talking about the unsupervised flood mapping that makes use of localized morphological active contour model, right. So, this particular slide gives you the idea how optical and microwave remote sensing both are used in this study, right. This particular slide will try to provide you the information how Sentinel-1 data, that is a microwave data, is being used in flood studies, right. So, if you are interested, you can refer to this paper and read more about it. Then comes the digital elevation model, which is one of the very important parameter in flood studies. So, we all know the digital elevation model represents height information, that is in the z value. X, y will be location and z will be your height information, along with latitude and longitude of the topography. And here this slope, aspect and basin information are extracted, right. So, you can easily extract the slope, aspect and the basin information, or the watershed boundary can be delineated using this digital elevation model. And there are many digital elevations are available nowadays freely in the public domain. You just have to register and download the data. This is one example of flood inundation mapping. So, this is from NRSC again. This is again another example from NRSC work. So, useful flood assessment through UAV. Now, when we talk about the UAV, sometimes what happen, the microwave sensors are not passing through that particular area and the optical remote sensing sensors are not able to capture the data because of the bad weather condition. So, in such situation, UAVs will be your third eye, right. So, it helps you to provide the accurate digital elevation model, right, and DTM, digital terrain models. It improved hydraulic modeling, then real time inundation mapping that will be able to capture, monitoring the structures to identify potential breaching zone, monitoring channel morphology changes, easier search and rescue operation, because this is very important to save the life and property, right. Vulnerability mapping become easier with this because you have high resolution DM, DTM and the visible or optical data sets, right. So, here this is one example how this UAV data sets are used. Here you can generate the point clouds, right. Then you can edit them and you can generate the DM, right. Then comes the LIDAR. So, topographic mapping using LIDAR data that provides you the higher accuracy digital elevation model. So, this LIDAR is very accurate and the cost effective and the predominant source of topographic data. Nowadays, it is very common and the floodplain delineation will be very easy, right. Now, let us talk about the ground based observation to identify the floods. So, these are sites on a stream or river where the systematic observation of the gauge height, that is water level, and discharge, that is flow rate, are measured. So, here you can have the manual station or here you can have the real time station, that is the automated one, right. So, here this is from 2 locations that is available in this particular website. Weather station and measurement of rainfall. A rain gauge measures the rainfall over a particular area in given time period, and the different types of rain gauges which are used for the point precipitation measurement. So, here we are talking about the in situ measurement. So, we have cylindrical container type, recording weighing type, float type or tipping bucket type, right. So, these are used for the point precipitation measurement. Then weather station and measurement of rainfall, the estimation of aerial precipitation, that is very important, because when we are working with the spatial data, when we are utilizing the remote sensing data, we should also have the rainfall for each of the pixel. So, then we can go for the aerial precipitation measurement. So, the better estimation of true volume over a given area, because point measurements are limited to that particular location, right. But when we talk about the aerial coverage, that means for each pixel you are having the precipitation information, that will be more accurate to calculate the total precipitation in that particular catchment. So, dense network of point measurements are required to generate such high spatial data sets, or we need to have the radar estimate. So, here the radar will be used to estimate the precipitation. So, when we talk about this aerial precipitation, we use different methods to generate the high spatial resolution rainfall data set from this radar estimate, right. Then comes the water sensor that we are using. So, it detects the rise in water levels, because that is one of the very important indicator, what is the situation at the ground in the river, right. Then automated alert can be triggered before flood water breaches the danger level. Then timely evacuation is possible. Why? Because if we talk about this particular section, suppose here we have put a sensor. If this goes beyond this, then immediately it will start giving the alerts, right. So, we will not wait for it to reach to this particular level, and then we will also inquire what is the situation at the upstream, right. So, advanced surveying equipment used in flood measurement. So, here you have the pressure transducers, right, which is connected through cable, and we have the data logger, and then crest stage and staff gauges, right, and it goes to this station and then it will be relayed, right. That means it will be transmitted. So, this will help to intimate the people living in that particular area that the river is going beyond this particular level. So, we should be careful, right. Integration of hydrological and hydraulic modeling. So, when we talk about this flood modeling tool, we have 2 different types, hydrological model and then hydraulic model, right. So, here the different methods or different softwares which are available commercially to evaluate the potential of flood vulnerability for particular area, and these 2 models will give you the output, and the output models can be studied together, and then flood hazard map can be generated, that will be very accurate, right. Then comes the flood hazard and risk mapping. So, here the flood hazard and risk mapping, it has importance in the analysis of flood risk. It helps to estimate the spatial extent of the flood characteristic such as depth, frequency and velocity, useful for flood management practices, right. So, these are the suggested readings, and I hope you will go through these papers, because this will help you to gain more information about the flood studies used with different method. So, these references are used in this particular lecture, and you can go through them, because they will explain all the details of the models or the various models used in their study. Thank you very much.